Let's have a little fun here. Um, I want you to think and maybe kind of have a discussion. I can take a poll initially, but on average, who do you think consumes more energy per day? A vegan driving a Ford F-150 Raptor or a cyclist that's on a paleo diet? Um,
Vegan.
so somebody said vegan. I can't see video right now because my Zoom settings are annoying.
I would say the cyclist.
I would say the vegan, but if I remember correctly, if we're talking about food and how usually how food works and when it comes to transferring up the food chain, is it like the higher you go, like for example, if if a rabbit eats, say, like greens, grass, whatever, they're getting the rabbit's getting a lot of energy, but or energy or nutrients. But if a wolf kills a rabbit and eats the rabbit, isn't the wolf only getting like the energy, whatever energy that the rabbit uh gained from eating the greens or the grass, it loses like 10% of that whenever the wolf eats it.
Yeah, that's a really good point. So what Slater is addressing is trophic levels. Each time you go up a trophic level, that is, go down the food chain, 90% of that food energy is lost to waste heat, to entropy. That is not taken into consideration in this analysis, even though it's very interesting. That's kind of assumed to be, well, at least at the initial trophic level, like free energy from the sun. But I suppose if we got into factory farming and things like that, then it'd be a very different story. I'm only assuming the energy required to produce the food and deliver it. And I didn't even think about like refrigeration and transportation and other those phases. Mainly just the production of these two different kinds of food. It looks like a lot of people are saying cyclist, and I think that too, just because we hear how horrible the meat industry is and how carbon intensive it is. It's not necessarily the most energy intensive, though. It's certainly more energy intensive than a vegetarian or vegan diet. But
I said cyclist because I was kind of assuming this was a trick question with the car.
Exactly. That's what happens every time. You guys, you're too smart. Think of how big this truck is and how much energy it takes to move it. One assumption I failed to mention is that are they going the same distance? Let's assume they both live, in downtown Bellingham and are commuting up to Western. So maybe they have a 3-mile total commute per day. So it wasn't a trick question. This is a huge piece of machinery, and it gets very poor fuel efficiency, and so it's going to consume a lot of energy. But we'll get back to that in a second. But already I can tell that a lot of good discussion is going on. Yeah, we'll get back to it in a sec. So I'm going to share my screen again, and I won't be able to see you anymore, but I'll make sure the chat's still open. If I can figure out that Zoom issue by the end of next class. All right. So moving on to big idea 1, personal energy use. So humans are exosomatic. What does that mean? It means, exo means outside of, somatic means metabolism. So we metabolize outside of our bodies. And that's a pretty unique thing. Not really any other species do that. If you want to be like really annoying at a party, you could say, what actually defines a human? Is it our language abilities? Probably not. There are many species that have language. Is it our tool use? Probably not. There's evidence of many species using tools. But the fact that we use energy outside of our body is very unique. So all the other animals, they consume energy and they use it to repair their own cells. They use it to grow and they use it to reproduce. Humans use a tremendous amount of energy outside of our bodies. So in developed nations such as ours, what factor, like how many multiples beyond our current energy, our metabolic energy use that we eat, do we use outside of our body? So, I use energy to do laundry. I use energy to drive a car. I use energy right now with my computer. So how many, say like my diet is 1 unit of energy, how many more units of energy outside of my body do I consume per day?
I'll say 100.
That is a good guess.
I'm trying to think kind of like I'm just kind of wild guessing there.
That's good. That's the first start. Any other guesses? So 100 is really close. The actual answer is 141, I believe. Come on, slideshow. Yeah, 140. But that's still incredible. It means that there's like 140 robots consuming the same energy as you, performing all sorts of tasks for you. They're giving you information, they're keeping your house clean, they're cleaning your dishes, they're moving you around, they're moving goods from far away to your house. There's big power plants off in the distance, keeping your lights on and keeping you cool or hot. So that you have this tremendous advantage from all this energy afforded to you per day. All right, so in this class, it is a science or math, GUR, so we will do a little math. I will try not to make it be too crazy at all, and you can always come to me for help. And again, we'll do study sessions online together to go through all the homeworks. And I'll even help with the midterm and final. Okay, so units are the way scientists measure everything. And units can be in many different categories. The ones that you're probably most familiar with are mass, or colloquially we say weight, distance, so how far something away is, and what's another one we think of a lot? Volume, like how much liquid is contained in a can or something like that. The units for energy are tricky, and there's many different kinds. So let's go through this a little slowly. But keeping track of your units is actually more important than keeping track of actual values, actual numbers. And there's this cautionary tale. The Mars Polar Orbiter was launched in 1998 from America, from Houston, or from Florida. And it takes 6 months or so to get to Mars. And as it approached Mars, the side of Earth that was facing Mars was Australia. So it was sending the steering information, the steering algorithms to the spacecraft as it was approaching Mars. And it sent the information in newtons, which are about 4.5 times more powerful of a force than a pound force, the American units that the spacecraft was programmed in Pasadena. And so the spacecraft accelerated far too rapidly and crashed into the North Pole of Mars. And you can actually see like this cartoon crater on the North Pole of Mars now. So that's sad. That cost a lot of money and was a tremendous waste of scientific expense. So keeping track of units is really important. The first 2 chapters of the book that I recommended for this class, David MacKay's Sustainable Energy Without Hot Air, details energy units really well. And so I recommend you read that. It's free. It's at withouthotair.com, or you can get it for like $30 on Amazon if you want a paper copy. All right. The energy unit in this book is cumbersome. It's a kilowatt hour. And so we'll unpack this. So what is a kilowatt hour? Energy has many different metrics, rulers. Why is this the case? It's only been about for 200 years that we understood that all these different types of energy were the same thing, that they're energy. So heat energy, light energy, electrical energy, radiation, potential energy, nuclear energy, all these different things had their own units based on the kind of energy they were or the energy carrier that they were. So if we're talking about heat, the French used calorie, or the English used British thermal units. If we're talking about, I mean, even today, many people describe energy in barrel of oil equivalents. All the oil majors do that. So, be like, society runs on 10 to the 15 barrels of oil per day. What does that even mean? The unit we'll use is a kilowatt hour because it's a very human-sized unit, and you'll begin to appreciate that. So some of the units you might come across for energy are a joule, a kilowatt hour, a kilocal. That's what you measure your food in. We call it calories, but they're actually 1,000 calories. BTU, that's what you'll buy natural gas in usually. A therm is 100,000 BTUs. It's really awkward. Quad is a quadrillion barrels of oil. Really stupid unit, but it's widely used. Mega barrels, etc. Let's start from the beginning. So energy, the actual fundamental units of energy is pure work from a physical definition. And so work equals force times distance. You may have heard that before. And the standard unit for energy is the joule. So energy is the capacity to do work. It's an abstract concept, but that's what energy is. If you have energy, you can change the environment. You can do work on the environment. You can make the environment look different than it does today. So work equals force times distance. And energy, a joule, is the energy, the standard international unit for energy. And so a joule, in terms of standard international units, will equal 1 Newton of force multiplied by 1 meter of distance. We can bust open Newtons and know that from Newton's second law, force equals mass times acceleration. This 1 Newton force equals a mass times an acceleration times a distance. And so we can define a joule using these standard international units. And a good mnemonic, a good trick for remembering what a joule is, it's the amount of energy required to lift an apple from the floor to a desk. So an apple weighs about 100 grams. And if we lift it 1 meters, then in standard international units, 100 grams is a tenth of a kilogram. Kilo, remember, means 1,000. And so 100 grams is 1/10 of 1,000. So 0.1 kilograms times the acceleration due to gravity. That's what we're fighting against when we lift that apple away from the center of the earth. So that's about 10. So 0.1 times 10 is about 1. Times 1 meter is again 1. And so that's 1 joule is the energy required to lift an apple from the floor to a desk. And in specific standard international units, it's 1 kilogram meter squared per second squared. But again, that's pretty ugly units. So let's just call it a joule. And that's what we do. All right. So again, before we get to what a kilowatt hour is, we need to define a few other things. Power is the flow of energy over time. Journalists, scientists, colloquial language gets us confused all the time. So energy is how much capability you have to do work. Power is that flow of energy over time. So how much time does it take to do a certain amount of work, to move a certain amount of energy? You could think of it like a river. Energy is how much water is in the river, and power is how much water passes through a given point on the bank per second. So the definition for power is a watt, and a watt is 1 joule per second, a flow of energy over time, energy divided by time. Power equals energy over time. And these are the two dead white dudes that define some of these things. Joule's experiment was pretty cool. He figured out that heat energy and mechanical energy are the same thing. He was the first one to kind of realize that the energy of motion is associated with the energy of heat, or at least the first one to define it fundamentally. I mean, I think a lot of people knew that motion could turn into heat for a long time, but he defined it. with an experiment where he just stirred water like a madman until it heated up by 1 degree. Okay, so in terms of a picture, energy would be how much oil or whatever is in this bucket, and power would be that flow of energy over time. So that flow of energy of oil. So again, power, 1 watt equals 1 joule over 1 second. And we can rearrange this. We can say time equals energy divided by power. So what's that kind of saying? It's kind of be like saying, how long will my battery last? Well, it depends on how much energy is in the battery and how much power is being pulled out of that battery. It begins to make intuitive sense when you think of it in real world examples like that. Okay, well, what's a kilowatt hour? So energy, again, has all these different units. We learned that a joule is a Newton meter. It's like lifting an apple from a desk. A watt is a power unit. It's energy per second, or a joule per second. And if we rearrange these things, put time from the denominator up here on this side of the equation on the left-hand side, then we have power times time equals energy. And so we can play with that and say, well, a watt times 1 second would equal a joule. Maybe I'll annotate that a little bit. Let's see. Oh, I can only write on one side of the screen. I think what happened was I started Zoom when my monitors were flipped because my display drivers updated. So I don't know how I'll be able to do that. I'll work on annotating it next time. We'll just do a quick rehash of what all this stuff is. All right, so back to the lecture. Okay. So if we rearrange this equation back here and say watt times second, or second times watt, however that's easiest for you to visualize, equals a joule. And similarly, you could use a different unit for time and say a watt hour. So that would be 1 watt of power multiplied by how many seconds? Well, there's 60 seconds per minute and 60 minutes per hour. So that would be 60 times 60. Well, 6 times 6 is 36. We have 2 zeros there from the 260s, would be 3,600 seconds. So watt hour is 3,600 joules. We're almost there. So watt hour is 3,600 joules. Therefore, 1 watt hour equals 3,600 joules. And we know a kilo from our drug dealing days equals 1,000. So therefore, a kilowatt hour equals 3,600 joules times 1,000 equals 3,600,000 joules. That's a kilowatt hour. That's a kilowatt of power flowing for the course of an hour equals 3.6 million joules. That's a tremendous amount of energy, right? That's lifting that apple 3,600,000 times. That's actually something that, you know, your refrigerator will consume 2-3 kilowatt hours per day. And that's, you know, testament to how much energy in abundance that we have in society, or at least in developed nations. So 1 kilowatt hour, it's a unit of energy, even though it has that watt sound to it. So you think power, power is defined in watts, or a power unit is a watt. But because it's multiplied by time, watt times hour, power times time, it's actually an energy unit. So kilowatt hour is a measure of energy. And specifically, it's 3.6 million joules, or 3.6 megajoules. Mega stands for a million in the Greek prefix system. You go kilo is 1,000, mega is a million, giga is a billion, tera is a trillion, etc. Any questions about all of this? Anybody freaking out about the math? Again, this all is in tremendous detail in McKay's Sustainability Without Hot Air, that first chapter or two.
Just a clarification. So the time unit, it's in seconds. Is that like for when you're doing like?
Yeah, the standard international units for time is a second. And so that's why a kilowatt hour is 3.6 million joules, because you get 3,600 seconds in an hour. 60 seconds per minute times 60 minutes equals 3,600. Multiplied by 1,000 from the kilo, you get that 3.6 million. Okay. I switched around my screens. Let's see if this helps. I'll share screen number 2. And y'all still disappeared. All right. Chat's open. All right, let's go to the next slide. So let's go back to this paleo diet on a cyclist paleo diet versus a vegan car driver. And this is, my efforts did not work at all. I'll just share screen 1 again. Okay, so each American drives about 1,000 miles or 10,000 miles per year. So if we convert from miles to kilometers, so we would multiply by 1 over 0.6, there's 1 mile per 0.6 kilometers. And then we divide that by 365 days per year, we would see that that's about 44 kilometers per day. The average fuel economy is 17 miles per gallon. You know, something like this Honda Civic would do far better than that. But this average fuel economy is brought down by the fact that the most popular car in America, or vehicle in America, the most purchased vehicle in America, any guesses?
A truck.
Yeah, it's the Ford F-150. It's the most sold vehicle in America per year. But they're making an electric one next year. That's pretty dope. All right, so if we think about how much energy the person driving the car would use per day, we can take energy per day. So it's 44 kilometers per day divided by 7 kilometers per liter of fuel. We know that there's 10 kilowatt hours of energy per liter of unleaded gasoline. That's just, you know, the heat potential of that fuel if we measured it. Will we get into electric cars versus gas cars and energy usage this quarter? Sure. Yeah, I think we should do that during an efficiency lecture. The great thing about the summer sessions and this class size is we really can begin to tailor it to what you all desire. More on that in a little while. And so if we crank through this math, we see that this car consumes 63 kilowatt hours per day. That F-150 or the Raptor, which is the like super tricked out F-150, gets 11 miles per gallon. And so this would grow to, you know, a factor of like 1/3 greater. So it'd be like, you know, 80 something kilowatt hours per day. And no shame on the F-150 Raptor. I think that's an awesome truck. I just can't afford it. Okay. Now let's switch over to diet. So minimum human total daily energy demand for typical American is 2,600 calories. So that's how many calories an American needs to neither gain nor lose weight. And if we convert from calories to kilowatt hours. And we'll do all this in subsequent lectures, but we're just having fun exploring some of these units and thinking about, you know, a real life problem here. It's 3 kilowatt hours per day. That's the energy equivalent. 2,600 calories is the energetic equivalent of 3 kilowatt hours. If you consume milk, so milk or cheese products, you need to add 1.5 kilowatt hours per day, because now you need to keep a dairy cow alive somewhere. Maybe not you specifically, but someone's keeping a cow alive, and that takes energy. If you eat eggs, you need to add another kilowatt hour per day. And that's because someone somewhere is keeping hens alive. Meat, you need to add 8 kilowatt hours per day. Again, because you're keeping pigs and chickens and cows alive somewhere. And you double this if it's all cow. And that's because cows are very energy intensive animals, because they're huge. And yeah. Fertilizer and farming. So fertilizer is basically natural gas. You take natural gas, you combust it with steam in an oxygen or nitrogen rich atmosphere, and you make ammonium nitrate. And so that's why Albert Bartlett, he's a physicist. Physicists are kind of buzzkills, but anyways, I'm a physicist myself. Modern agriculture is the use of land to convert petroleum into food. And what he's saying is that we're taking natural gas and making fertilizer and allowing the land to be productive in a, you know, Western capital industrial sense. Lab grown meat, I don't know. That's a really good question. And again, I'm still debating whether or not to have like a formal final in this class or have some project-based things, because it's a smaller class. Like, you know, perhaps one of you would like to make a podcast on energy equity or carbon mitigation technique, or maybe somebody wants to write, you know, a short 2-page paper on the energy requirements for lab grown meat. So different options. We'll talk about it later. And then we could share each other's results the last day instead of doing a boring final. So total is about 12 kilowatt hours per day per American. That's how, so even though you consume 3 kilowatt hours per day, you need 12 kilowatt hours a day of energy production somewhere to grow all your food. If you're strictly vegetarian, that drops down to 5 kilowatt hours per day. If you're just like hardcore Joe Rogan, then you're going to be required 20 kilowatt hours per day being to grow all that cow somewhere. So back to this paleo versus vegan question. So the vegan driving a Ford F-150 Raptor is about 100 kilowatt hours per day. Cyclist on a paleo diet, 30 kilowatt hours per day. In a former class, a student raised the very excellent point that this person is going to be consuming a lot more than 2,600 calories or 3 kilowatt hours per day, because they are burning so many calories riding their bike around. And so we could double that and say it's about 60 kilowatt hours per day. And so it's about a push, but when it comes down to it, then the vegan driving Ford F-150 Raptor is definitely going to consume more energy on a daily basis over the long term. And that's because the amount of energy required to shove this thing around, to move it around is tremendous. It's just weighs way more than that bicycle.
I'm assuming the Ford F-150 is a lot more costly than, or a lot more energy intensive than the car that we calculated on the cars page then?
Yes. Yep. Yeah. So this is about 85 plus 15 or so. But yeah, if it's strictly vegan, then maybe it'd be just like plus 10 or something. And if this person's consuming a lot more calories, then it could be higher. But it's just a good thought experiment to play with some of these concepts and ideas. This question was actually motivated back when I lived in California. I lived in San Francisco in SF, and I'd take the Caltrain down to Palo Alto, whereas when I was postdoc down at Stanford. And that Caltrain, the last 2 cars were bike cars, and this smelled pretty bad. But anyways, a lot of us bike commuters would get in there, and usually it's kind of younger, climate conscientious or nerdy folks, it seemed like. And it was often populated with a bunch of people working at Google and Facebook, because they're, in Menlo Park and Mountain View respectively, all in the same area down there. And oftentimes interesting conversations would happen on the commute back to the city. Usually the rich Google kids would have a bunch of beer and hand it out, and we'd have fun. But one time this question got asked, like, this specific question got asked, like, okay, we're doing all these good things. We're riding our bikes, we're riding the train, we're not driving cars. Are we really that good? How important is our diet? And so people were going back and forth, back and forth. And then I shut down the joke, the conversation with a dark joke by saying that no matter what, the vegan driving the Ford F-150 Raptor is going to consume more energy because they'll run over the cyclist and they'll no longer consume energy anymore. Womp womp. That's not true. Cyclists, we stick together. In terms of caloric intake and energy, which is more efficient, vegetables and greens or meat? Good question.
I asked this question because I want to try to. There's a question I asked about the trophic levels.
Yeah, it depends on what we mean by more efficient. If we're talking about total like life cycle energy consumption from that blade of grass to your belly, then definitely vegetables are more efficient because there's not as much energy losses along those trophic levels. If we're talking about what's the most energy efficient thing for you to eat, well, I mean, meat, like just a stick of butter, like that's so energy dense. You can bring one stick of butter and that you can live off that for the entire day. It's not maybe the most nutritious, but it's certainly very energy dense and therefore efficient. You need to
Soylent
eat
Green in butter form.
Yeah, you need to eat a lot more veggies and greens to satisfy your total daily caloric demands.
But if you were, say, if you're a cyclist, right? If you're a cyclist and you needed like a lot of energy to, to pedal that thing to go from point A to point B, would it be a lot smarter to eat meat in that regard to power yourself?
Yeah, I suppose there's probably an argument for that. Perhaps fat rich fish like salmon would probably be the best bet. You could have a granola bar rolled in coconut oil. That way you could still be vegetarian, but carry a lot of calories around with you at a specific time. These are all interesting questions where there's not like truly an obvious answer. And this is where things like measuring, the carbon emissions or methane emissions from these different food processes can be perhaps more informative than just thinking about pure cumulative energy demand in terms of environmental harm and justice.
What about rice fried in coconut oil? That sounds pretty good.
Yeah, that would be a pretty energy efficient and low cumulative energy demand food product. Yeah, perhaps Thai or Vietnamese food with a little white fish is probably some of the best you could do in terms of environmental harm and energy efficiency. All right, but I'm getting a little out of my knowledge base here. Okay, so that was that. Let me show the syllabus and the schedule. We'll show the schedule first. I think that'll be a little more informative. This over here, screen share. All right, so y'all can see this, I hope. Here's the class schedule. It's color coded by week. So this is week 1 that we're in here, and there's 6 weeks. And this first week is going to be lecture heavy because we're just getting into it. And so we're going to talk all about personal energy use. So today we did a little thought experiment with food and transportation. And we're going to dive more deeply into heat, the second half of this lecture. Then we'll talk about our gadgets and all our stuff. on Thursday. First homework's been sent out. It'll be due a week from now at midnight, and that'll be after this live study session that I'll also record. Let me think. So I'll have to try to post that right away after I record that session. And then we'll get into thermodynamics. So we'll think about energy quality. So not all forms of energy are created equal. Some are more useful to society than others. Electricity is the most useful form of energy. We can convert that pretty easily into all the other forms, whereas something like low-grade waste heat, not terribly useful. Like I pour that on my computer, it's not going to work. Then we'll get into societal scale energy. So we'll jump from personal to societal, think about how much energy it takes to run nation states and the world at large. What are some of the fundamental inputs to those energy requirements? And then we'll spend 2 weeks talking about the consequences of that energy use, mainly climate change being the largest one. And what are some potential solutions to that? And then we'll spend the last part of the class talking about, ways to have our cake and eat it too, to consume a lot of energy and not trash the place at the same time. And halfway through, we'll have a midterm, and you'll have a week to take that, open book, open notes, just by yourself. Open internet, but not internet forums. I don't want real-time communication on the internet for your test. And then we'll have a open book, open note final for that last week, or we may choose to do a podcast project or short term paper, that sort of thing. So that's the schedule. There'll be 1, 2, 3 homeworks and a quiz associated with thermodynamics. Now let's get into the syllabus real quick. Blah, 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 boring. This is what you care about. 50% of your grade will be from the assignments. Right now there's only 3, so maybe that quiz will count as one of those assignments. Don't shrug them off, because each one of them is 12.5% of your grades. So if you don't turn in one, the best grade you can get is B+. That's assuming you get a perfect on everything else. I will not grade these homeworks very harshly at all. They're a learning tool, and so I want to see effort, I want to see thought, and again, we'll work on them together. So there's really no reason why you shouldn't be able to get all these in, unless there's some sort of medical emergency. And of course, if there is, please let me know. Historically, I had a podcast project, but in this short time frame, it's difficult to see. I feel like it would be unfair to require all of you to do a podcast in just like short 2 weeks or something. But if that's your gig, then by all means, go for it, and we can do that in lieu of the final. Midterm, there will definitely be a midterm. Will be 25% of your grade, and then the final will be 25% of your grade, or the project if we go that route. So give some thought on that project versus final, and we'll talk about it over the next week or two. Blah, blah, blah. Here's some norms that we already discussed. Don't cheat on the midterm. I hate it when that happens, but here's some academic policies associated with cheating. So it's right here, right up front. So there'll be consequences if you do so. But I'm not worried about it. Okay, any questions about that stuff? All right, let's take a 10-minute break, and then we'll get into heat. I'm gonna do something crazy. I'm gonna turn off this Zoom session. I'm gonna kill it, and so please join back. I'm doing that in hopes to reset Zoom so I can get the video working better.
Okay.
So I will see you at 10:50. Zoom will be back on by, I'll see you at 11 o'clock. Zoom will be back on by 10:55.
Okay.
Cool.